Nice cup of tepid tea. Try and make this as short as possible. Just go over how to use these equations, the essential key facts that we're missing from this set of formula sheet. So we're dealing first of all with plane stress problems. Good example would be a balloon skin. So you're blowing up balloon skin or a thin piece of paper, and the force that I might apply in the Z direction would push through my paper. So I cannot have any force overall pushing from my paper. For your balloon skin, that doesn't seem to make sense because you've obviously got a lot of pressure inside your balloon, but the elasticity of the balloon on the outside is pushing the pressure, air pressure on the inside. So overall the force is zero. So overall you've got a zero force in the Z direction, and you call that plane stress. What you got to do is think of the word zero in front of these terms. So the other term you might come on to is called plane strain, and again think to yourself the word zero plane strain. So that means in that particular case, in the Z direction, we'd get no movement, but we would get stress. What does this equation mean? Well, for this I need to start drawing what's called my stress state element. Normally we just show a square. We show a force being pulled off in the X direction, so we're taking that to be our X direction, and a force being pulled off in the Y direction, and then another force which will represent shear, and the shear force behaving on this plane side rather, it has to be the same as this side. Now all of these will have mirror little stresses. Okay, so stress is a bit like forces. So here that we have one down here, here we have one down here. So this equals this, okay, in terms of magnitude. This equals this in terms of magnitude, obviously cancelling out. This equals this in terms of magnitude, obviously cancelling out. And why this has to equal this going around the corner is to stop rotation. So it can't be rotating, and we don't have any overall force. And again, this one is going to be balancing this one, and this one's going to be balancing this one. So since the red and the black values all have to equal one another, normally you don't write down the red bit, just write down the black values. So then you would say what your stress values are, so how much shear stress we're going to get. So we're going to have 100 pascals of shear stress. We're going to have 200 pascals going in the X direction and 300 pascals going in the Y direction. So that's how these things work. So you've got 100 shear stress, you've got 200 tensile stress going in the X direction, and you've got 300 tensile stress going off in the Y direction. Flip these around, they become negative and they become compressive stresses. So what does this value here give me? That value there will tell me where the principal compressive stroke tensile stress is behaving. So in this particular case, if I put the numbers in, I would imagine I'm going to get an angle around about going off in this direction. So if I'm pulling in 200 in this direction, 300 in this direction, and I'm shearing my element, so here my little diagram here, so I'm doing a little bit of this, doing a bit of this in that in the X direction and a bit more in the Y direction. What ends up happening will give me what? So we would have tan 2 theta P equals 2 times 100 divided by 200 to take away 300, so that gives me -2, and that gives me 2 theta P is -63 degrees. And don't forget that you might need to plus 180 for your other axis. So the other thing to note that we don't have here is we're using tan quite a lot. So what does the tan look like? It looks something like this. So if I find a solution here, I will have another solution 180 degrees added on. And that will give me my other principal angle here. So here we've got one of -63 degrees. Divide that by 2. So I've got one principal value of -31.5 degrees. If I plus the 180, my other solution would be -63 plus 180 divided by 2. And that gives me 58.5 degrees. And normally we like to take the 0 degrees to be going in the east direction. So here 58 degrees is really the one I want, isn't it? So it's 58.5 degrees. So that will be, taking all these forces together, that would be the main direction things are being, in this case, pulled apart. And then we could say that the other direction is going to be going off in that direction there. So be careful, not necessarily your first solution will be actually the primary direction of interest, really. It's more interested in this result than this result. So that's what that tan equation is for, and obviously that's very useful for when you want to know about pulling things apart. What's this useful for? This one here. So this is referring to the angle of maximum shear, and that's useful for when you're tearing things apart. So fracture mechanics, fatigue mechanics, these are normally things which get torn apart, and we would like to know what direction that occurs in. So you can do the same thing. What you'd normally find is you will find that the shearing action tends to be at a 45 degrees angle away from your principal pulling apart, and you'll find this for in tensile experiments. So tensile experiments, you tend to see this action where we've got a bit of necking going on, and depends on what the element looks like, but there'll be a crack and a cupping effect. So if you get the ductility right and whatnot, you'll tend to get this fracture, which is a kind of 45 degrees angle, and that's because these things are fractured along a shearing line. Things can fracture along shearing lines. They can also, obviously, they could fracture in a brittle sense. and they could fracture like that. So that they don't necessarily fracture at this 45 degrees, but a lot of things that are quite ductile do. Right, we're getting away from my game plan, which was just really go through the equations. So that tells me the shearing angle. What about this thing here? Okay, so this thing here is to try and recast your equations to get rid of your shearing value. How does that work? Well, let's work this out. So normally, good plan is to work out your numbers for your left bit and for your right bit. So here we've got 200 plus 300 divided by 2, so 250. And then do a plus or minus. So I've got 200, take away 300, divided by 2. When I square it, it should become positive, plus the 100 squared, take the square root of that, and then I end up with 111.80. So the maximum obviously will be the plus term, because this is a plus term. So that's 361.8. And the smaller value will be 138.2. So coming back to this diagram, that's telling me that we can take this element and say this is the same as a stress that's being pulled off in this direction by 361.8 pascals, and another stress going down in this direction of 138.2 pascals, and we've completely got rid of the shearing action. Okay. The next thing is, let's say it's going to start shearing. What is the maximum amount of shearing that it's going to have along this angle? So we could work out the angle. Let's work out the angle actually. So that's going to give me tan equals 200, take away 300, all divided by 200 again. So that gives me 2 theta share will be 26.565, and we want to check out the other solution. So we got one shearing action at 13.3 degrees, and the other one, the other possible one, and when things shear, they could tend to shear in either direction, 103 degrees. Okay, so if it's going to shear along this, in this case it would be quite shallow, and if it will be shearing along this line. How much shearing stress is being experienced, and that's what we could use this for. So notice, it's one of the reasons why you want to work out these things individually, that this term here is just this term here. So the maximum amount of shearing that it's experiencing is 101.80. So now you can start doing some stress analysis. Perhaps that your element is more likely to shear than get pulled apart. So you can compare those two terms and then start to come to some conclusions. So that's what those equations are used for. These equations are used to literally transpose your angle to your stresses to a different angle. So that's quite straightforward. So you just need to say what your new angle is, put them in there, take your original values here. So here, in this case, that would be 100 would go in there. This is 200 going in to here, and 300 going into here. And then whatever angle that you're looking at, let's say you're doing kind of the experiment where you want to reorientate your stresses, say at a 45 degrees angle probably. You could then start putting in those values there to get what the stress is and how the strain, shear stress is